Welcome back to ECE 442-542. I have quite a list of goals. Hopefully we will get through some of those. Before we talk about goals, just as a reminder, the passport is due today and that can be turned in to the Dropbox on D2L. The Proctor Agreement form, if you're an online student, I need you to submit that by a week from today. Homework number 1 is due in a week. Z-transform references, which is where we're headed in unit number 2, those are now available. If you want to start reading ahead, you can. Those are available in unit number 2. That's on the content page of D2L. And just as a warning, exam number 1 is basically 2 weeks away, 2 weeks from Wednesday, just to remind you, just to get you thinking about where we are in the semester. And we'll have homework number 2 due a week after homework number 1. So homework number 2 will be on the 6th of February. That's not on that announcement page, but it's implicitly there. Goals for today. We want to pick up where we left off last time. We talked about solving homogeneous linear difference equations. Today we will talk about non-homogeneous or linear difference equations that have forcing functions applied to them. We will talk about settling time, and that only really makes sense when we have a stable system. And when do we have a stable system in a z-domain system or in a discrete time setting? When is our system stable? Do you remember? We want our poles in the left half plane. We're in the continuous time. Now we'll show later this connection between the S-domain in the frequency and the Z-domain in the frequency, and we'll see that that left half plane gets mapped into the unit circle in the Z-plane. So now we want our poles to be inside the unit circle in order to have a stable system. If all of our poles are inside the unit circle, we will have a stable system, and sometimes it's nice to know when do you settle. At what time? And we might talk about different times. One might be the number of sample periods, which is capital N sub S, and another might actually be the actual time, which is the sampling period N sub S times, which is the number of sample periods N sub S times the sample period capital T. That gives you the actual time that you might sample, and we'll be going in this class versus if you had 441 or 541, we talked about a 2% tube. Let's change it up. Let's talk about a 1% tube that we want to be inside of when we then can denote when is our settling time. And I've just pictorially illustrated what we mean by settling time, or the number of sample periods to get within this 1% tube, or when do we get to 0.01 of our initial condition. And obviously this is concerned with no forcing function being applied. This is a initial condition problem, and we say, okay, we start the system, and when does it finally decay to 1% of where you started? That's our settling time. And that will be a part of problem number 4, which I reformatted a little bit to give you a connection with the reference material. They've changed which version the Osterman-Murray material is in, so I've simply given you a different link to the correct information now. But on part B is when you're doing this settling time problem. No input, but a non-zero initial condition. You want to determine when do you actually get to 1% of where you started, or 0.01 of capital N. And that's for a first order system, and so it's not that hard. You're just raising this system matrix A to higher and higher powers, and you want to know when does that power get to the point where we're at 1% of our initial condition. We'll talk about that hopefully today. We will also talk about block diagrams, and in particular in the discrete time setting. And if it's in the time domain, Then we will have delay blocks, and we will simply assign the outputs of these delay blocks to be our state variables. And once we've done that, we now have essentially a state space representation for a discrete time system. We could also talk about the frequency domain. We danced around in class. We said, oh, we're in the time domain. No, we're in the frequency domain. We want to be able to go back and forth, not only in continuous time. That was with the S and T. Now we want little n and z in the discrete time setting. And we want to be able to move back and forth between all four of those different representations or descriptions. And we can quickly go from a time domain block diagram into a frequency domain block diagram by replacing the delay blocks. Like we replaced integrator blocks with 1 over s's, now we'll replace the delay blocks with 1 over z's, or z to the minus 1. Z to the minus 1 is a unit delay operator in the frequency domain. And we'll use that really before we even fully make the connection between the S-plane and the Z-plane, which is further down in our list of goals. But we'll show how we can use block diagram algebra to obtain the transfer function. We'll look at the interpretation of what this complex variable Z is. Just like S is a complex variable, Z is also a complex variable, which means we have a lot of different complex planes to keep track of. You could just think of them as different pages on in your notebook. Oh, here's the S-plane. That's a complex plane. Oh, here's the Z-plane. That's another page. It has a real part and an imaginary part. But that gives us a way of thinking about these poles in a complex plane. And that we will try to interpret for the complex variable Z, like hopefully you start to have or already have a feel for what this complex variable S looks like or what it does. Then we will talk about this connection between the S-plane and the Z-plane. I already said earlier today, just in going through these these goals, that stability in the Z-plane is inside the unit circle. In the continuous time domain, we had this infinitely big left half plane. Now we simply have this finite area that determines stability for a discrete time system. It's just the area of the unit circle. We want our poles inside that finite area to give us a stable system. Then a rule of thumb, and a lot of times you're uncomfortable with this because it's just basically a rule of thumb. It's not hard and fast. It's not an exact value, but it's something to connect with. If you wanted to sample a system, then if somebody knows what your closed loop bandwidth is, how fast you want this system to operate or behave, then sample at 30 times that, and there is your sampling frequency or your sample period. And they're all related by omega sub s, the sampling frequency in units of radians per second, is 2 pi f. That you should remember until you retire, just like Eli and Ice. Omega is 2 pi f, and for some of you, retirement might not be that far away. Everybody that I know now is retiring, so I guess all of you will be retiring in 3 or 4 years. It'll all be before I retire. I'm just really young. I wish. So 2 pi f, or you can relate that to the sample period, which is 2 pi over cap t, where the sample period now is in seconds. F sub s, the sampling frequency in cycles per second or hertz. You need to be able to go back and forth between those, where the sampling frequency in hertz is 1 over the sample period. And if you want to know what capital T is, then you don't just grab it out of the air. You say, how fast is my system going to be operating? I need to sample at 30 times the closed loop bandwidth. And we'll get a little bit more comfortable with what that closed loop bandwidth means if that doesn't mean anything to you now. That's okay. That was the promo. Wow. Now we need to get started. So, Let's move forward and talk about a non-homogeneous linear difference equation. If I could cover it up, I would. I can in class, but it still sort of projects through my hands. But before, what did we have? We had a homogeneous linear difference equation, which was the left-hand side set equal to 0. We did not have a forcing function. Now we have a non-homogeneous linear difference equation, which means we have something driving this system. In this case, we have a forcing function that's 1/2 to the n. And that's actually fairly easy to think about, but that's just an exponential decay. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. 1/2 to the 2 is 1/4. So you're not hitting this with much of an exciting system or signal, are you? It's decaying exponentially with time. But we want to know, can we now solve this forced differential equation? What's the procedure, or what's the process? We know how to find the homogeneous solution, meaning if I simply set this right-hand side to 0. But now we want to know, how do we generalize that when this right-hand side is something else? Right now, that's a pretty easy forcing function. It could be a decaying this is a decaying exponential. It could be a sinusoidally decaying exponential. It could be a sinusoid. It could be a lot of different things on that right-hand side. We need to know, how do we solve this no matter what that right-hand side is? To make that point, let me just remind us that the forcing function in this example is what I'm calling u sub f of n. In this case, is 1/2 to the n for n greater than or equal to -1. Remembering what we talked about Wednesday, which maybe you don't remember a thing, but we need to start remembering. We have an exam coming up. What was the homogeneous solution structure to this system? And you need to do that. If you have a non-homogeneous difference equation, the first thing you want to do is find your homogeneous solution structure. Don't find the homogeneous solution, just find the structure of that solution. Do you remember what that was? Let's call it x sub h for homogeneous of n. Do you remember what the structure was, or how to find it? We assumed a structure, let's say a times z to the n, and then we tried to find z's, didn't we? We found those z's to satisfy our characteristic equation. Somebody's playing the drums. I'm sorry, if you're listening to this online, you have no idea what I'm talking about, but somebody's pounding on the walls. They're just excited to solve the non-homogeneous linear difference equation. So let's solve it for them. We found the values of z, and those were -1 and -2. The structure then for the homogeneous is a1 times one of those z's, -1 to the n, plus a sub 2 times another one of those n's, which is the -2 raised to the n, and this is from before. If you've forgotten, hopefully you can go back into the notes and find that structure. What you have to pay attention to now is, if we have a forced difference equation, don't solve for a1 and a2 yet. Wait, hold off on it. Don't solve, because last time we did. We used our initial conditions to solve for a1 and a2. Let's not do that yet. We have to wait until we put in or find the complete solution structure, and then we'll solve for a1 and a2 using the initial conditions. Now, don't solve for a1 and a sub 2 until we find the structure of the complete solution. And the complete solution contains the homogeneous and the particular solutions. Let's look at the particular solution. We have the structure for the homogeneous. The particular solution structure, do you remember what you did in a differential equation class? If somebody said, what's the structure for the particular solution? If you don't, that's okay, but by exam number 1, you definitely need to know it for this class. Do you know what to maybe guess for that structure of the particular solution based on this non-homogeneous differential equation? The first thing that you do is you look at what's forcing your system and you say, oh, my particular solution usually will have that same structure. I say usually because if your homogeneous has the same structure of this, you need to make the particular solution independent, which means you need to add in some n, or an n squared, or an n cubed, just like you added in a t or a t squared to multiply the particular. In this case, 1/2 doesn't equal -1, and it doesn't equal -2, so we can just stick with 1/2. Our particular solution structure now, which I will denote as x sub p of n, is now going to be some constant, which we need to find. I'll just say a sub 3, since we've already used up a sub 1 and a sub 2, 1/2 to the n, where this is what I'm saying is the same structure as the forcing function. Yes, that's a poorly written subscript. That's an a sub 3. Well, now it's nothing, is it? Somehow it all disappeared. So let me slow down and write an a sub 3. Is that better? So this is the same structure, the 1/2 to the n, as the forcing function. And if it so happened that one of our homogeneous solutions or roots was 1/2, then we would have put in an a sub 3 times n, little n, times 1/2 to the n for our particular solution. We need it to be linearly independent of the different structures that we have to contend with. Now, what we want to do is now actually find that unknown coefficient a sub 3. But this a sub 3 needs to actually satisfy the governing difference equation, which we started with. So we need to find the value of a sub 3 that will satisfy this linear difference equation with the forcing function present. Let's now find a sub 3. Or we now use this structure, x sub p of n, into this forced linear difference equation. Meaning, when we see an x sub n, we replace it with x sub p of n, the structure that we're assuming. When we see an x sub n minus 1, we replace everywhere we have an n in the x sub p of n with n minus 1. n minus 2, we replace n with n minus 2. And then we will only have one unknown in that equation, and it's a sub, and we can solve for that unknown, which is a sub 3. Doing that, we now say, oh, there's x sub p, and from our governing difference equation, we have a sub 3, 1/2 to the n. That's simply x sub p of n. Plus, what was the next one? That was 3 times x sub p of n minus 1. So we have 3, and what's x sub p of n minus 1 going to look like? What's a sub 3 at n minus 1? It wasn't a function of n, was it? So it's now a sub 3. 1/2 to the n minus 1. plus 2 a sub 3 1/2 to the n minus 2, and that's supposed to equal 1/2 to the n. And this needs to be true. A sub 3 needs to satisfy this for all values of little n. Well, let's pick a convenient value of little n and solve for a sub 3. It has to be true for all. Let's just pick one. And an easy one would be n equal to 0. Since we said this is going to be true for n greater than or equal to minus 1 to begin with, let's just now say with little n equal to 0, what do we have? Now we have a sub 3. I apologize for my 3's. For some reason, I can't seem to write a very clean or legible 3. But what do I multiply that by? 1/2 to the 0, which is 1. So I'm done. What about the next one? I'm replacing n everywhere with 0. This is now 1/2 to the minus 1. Putting in n equals 0. Plus 2 a sub 3 1/2 to the minus 2. Are we clear where these are coming from? Equal what's on the right-hand side. 1/2 to the 0, which is 1. And now all we have is one equation in the one unknown a sub 3. The 1/2 to the minus 1, what does that equal? 2. That's not too difficult. What about 1/2 to the minus 2? 4. So now we have 1 plus 2 times 3, 6. I can do this math even on my fingers. Plus 2 times 4, 8. I have 1 plus 6 plus 8. Is that 15? This now gives me 15 a sub 3 is equal to 1, or now I've found what that a sub 3 is. It's 1/15. And now I know what my particular solution is. It's now 1/15, 1/2 to the n. That's my particular solution for that given linear difference equation. What's my complete solution? And maybe you didn't like differential equations, but you're going to love linear difference equations, aren't you? These solutions you can actually kind of do. You don't have to integrate. You just plug in numbers, right? That's pretty easy to see what that solution is for the particular. What's the complete solution? That's the sum of the homogeneous and the particular. This is now just x sub h of n plus x sub p of n. And we know what that is. We now know the complete solution is x of n is a1 minus 1 to the n plus a sub 2 minus 2 to the n plus 1/15, 1/2 to the n. Now what do we do? A1 and A2 are unknowns, but can we find them? We're going to assume that we had the same initial conditions as before. I didn't say that going in, but now we would use the initial conditions given to us and solve for A1 and A2. We had 2 initial conditions. We can use those to solve for A1 and A2. We can now say solve A1 and a sub 2 with the initial conditions. And I know that you want to just run home and do this tonight, so I'm not going to spoil the fun. I'm just going to say you can do this on your own, but I'll give you the answer. Is that okay? Therefore, here's the answer. And you can check me. Sometimes I'm wrong. You can correct me if I'm wrong. Just don't do it live. Tell me in private. Then I won't be so upset. I take things very personal. So now what do we have? We have x of n is now minus 2/3 minus 1 to the n plus 24 over 15 minus 2 to the n plus 1 over 15 1/2 to the n. And now we have a closed form solution for x that satisfies that forced linear difference equation that we started with. Can you tell me what this is going to do as a function of question? What were the initial conditions again? I thought you had those memorized from Wednesday. I don't remember. That's why I was hoping you did. I think it might have been but check me on that. Okay, I think x of minus 1 was 0 and x of 0 was 1. Is that right? So those were the initial conditions that you would plug in. You would plug those in to this equation for x of n, and the only thing you don't know is a1 and a2. You're evaluating for particular values of n. You can use those, and then that allows you to solve for the minus 2/3 is a1 and the 24 over 15 is a sub 2. Did that help answer your question? So this tells you that you need to take thorough notes, because I may forget. Okay? Question? Pardon? Why are we using the n equals 0 value to find the particular solution? Was that the question? Because it was easy. We could use any value of n we wanted. We could have used n equal 1. N equal 1 wouldn't have been too hard, but some of the things sort of fell out, didn't it? The right-hand side was easier. Maybe it was a 1 instead of a 1/2. And the first term is now a 1 and not a 1/2 if we used n equal 1. But you better get the same answer, because this is supposed to be true for all values of n. And we just said use a convenient value for n. Other questions? I guess I should not be blind when I'm trying to ask for questions. Wow, some happy faces. Questions? How does this behave as a function of n? Can you tell me? If I give you an n, can you figure out what x, oh, that scared somebody. Can you figure out what x of n is? For any n, you can evaluate that expression. Yes? Now, what happens when n gets big? Can you see what happens? Throw away the back two terms, the rightmost terms, and what happens as n gets big? Do you ever settle? It's just bouncing, isn't it? Minus 1 plus 1, minus 1 plus 1, scaled by minus 2/3. It's just bouncing. So it's a sinusoid, essentially. It now includes some more. If we include that minus 2, what's happening? Now that's blowing up, isn't it? It's going to dominate that crazy forcing function that I introduced, 1/2 to the n. That's shrinking, isn't it, as n gets big? But which is going to dominate the behavior? The minus 2 mode, isn't it? It's going to swamp everything. The minus 1 is just going up and down. The 1/2 is going shrinking. And the minus 2 is going, right? It's just going crazy, popping back and forth from minus to plus, minus to plus. But that's the one that dominates the behavior. And you need to be thinking or understanding what might be happening for different values of n, for n, and in particular, the behavior for large n. Could we talk about a settling time for this particular X event? Does it ever settle? Even if we erased that middle of the three terms, does it ever settle? So if you had something that was bouncing around, sinusoidal, and it didn't decay, you couldn't talk about a settling time, could you? It's never going to a steady state. It just keeps ringing. It wouldn't make sense to talk about a settling time. So let's talk about a settling time. That means that we can't be dealing with poles on the unit circle, -1, or any particular value complex that might fall right on that unit circle, or anything outside the unit circle. As long as we're inside the unit circle, we can talk about settling time. Settling time, for the only time it really makes sense to talk about settling time is for stable discrete time systems. Just to mix it up a little bit so that you're not always thinking we keep repeating, let's just talk about a 1% settling time in this class. So if I talk about settling time this semester, it's a 1% settling time. Not a 2%, it's a 1%. And I think I saw a hand, even without glasses. Yes? Yes, so now a lot of times you'll hear people, if you have roots on the unit circle, somebody might say that's marginally stable, but you're never settling because you're just sitting. You're just bouncing, aren't you? You never decay, you never expand. So I prefer, if we're talking settling time, you have to be exclusively inside the unit circle, not on the unit circle itself. If you wanted to create an oscillator, then you would build a system that had roots on the imaginary, or on the unit circle. I said imaginary axis, then I'm in the S plane, aren't I? That's where you have an oscillator in continuous time. Here in discrete time, to have an oscillator, we would want our poles to be on the unit circle. And where they are would influence the frequency of that oscillation. Now that we're at -1, what's the frequency of that? Positive, negative, positive, negative, positive. That's pretty high, isn't it, as a frequency? We'll find that -1 is a high frequency signal in discrete time system, or when we have roots at -1. All right, so now let's consider our initial condition response, again, for stable systems. All of our roots are inside the unit circle. Let's consider the initial condition response. Or here, we want our input to equal 0, and we want our initial condition, let's say y of 0, to be something non-zero, let's say m, not equal to 0. And I may not even call it m. I may just say, let's just call it y of 0. And let's just, once you understand this, you get it, I hope. Let's just select a particular first-order system. Let's say that we now have y of n plus 1 is equal to a y of n, and let's just say a is 0.887. I don't know, I like 8, but I wanted to vary it, so I put a 7 in there. 0.887. Is that representative of a stable system? What are we looking for? What should A be if we had a stable system? Less than 1. And this is a very sort of trivial system because it's first order, isn't it? Our A matrix is a 1 by 1. It's a scalar. If our A matrix, which if it was 4 by 4, you would find the eigenvalues of that 4 by 4 matrix, and you would want all 4 of those eigenvalues to have a magnitude less than 1. And I say magnitude because they could be complex. But you would just find their distance from the origin, that's the magnitude, and you would want that magnitude of a complex number to be less than 1 for your 4 eigenvalues if you had an A matrix that was 4 by 4. Here it's 1 by 1 just so that we can get a feel for what's going on and we can easily draw that. For this system, let's find the settling time. You told me that it's stable since the magnitude of A is less than 1. And what does this, if you wanted to go home and sketch this on a napkin for your roommate, what would you draw? Because I know you want to just go home and show this off. Right? Wasn't that funny? But what is it? We now have y of 0, and then what happens? Where's y of 1? Is it there? Where is it? How big is it relative to y of 0? Here's how our system behaves. The next y is 0.887 times the previous y. So whatever y of 0 was, if it was 1, then the next one would be 0.887 times 1, or 89% of where we were. Then it's 89% of where we were. Then it's 89% of where we were for each step in, time instant in. Which means that it's just going to be going down. But eventually what we want is we want to determine when do we get inside this 1% tube. So this is representing 1% of y of 0, or this one is 0.01 y of 0. This one is minus 0.01 y of 0. We know we're not going to go there because we don't have any oscillation. It's a first order. But if it was second order, it could be bouncing around positive and negative. And that's why I'm indicating this lower bound of minus 0.01 times y of 0. Is it clear what that 1% tube represents? You want to know at what little n do we first come inside that tube? And that will be our settling time. Let's figure out how we can do that. We know the behavior. Y of 1 is A times y of 0. That's the governing difference equation. What's y of 2? Well, it's A, y of 1. But we can relate y of 1 we just did to y of 0. So this is A times A y of 0, or that's A squared y of 0. It's late, so I'm having trouble seeing a pattern. Teasing, but let's just humor me. So what's this? This is now A times y of 2, which is now A times A squared y of 0, or it's now A cubed y of 0. Do you see now what y of capital N will be? It's just A to the n y of 0. Don't you wish your differential equations were that easy? Now you know the generic structure for a first order difference equation. There it is, if it's non-forced. This would be the homogeneous solution structure. We want a 1% settling time. or we're actually looking for, or we want this y of n, which now let me say that's y of capital N. We want to know, when do we reach capital N to allow us to be less than 0.01 y of 0. That's the definition of our 1% settling time. Or we now know that y of capital N, we want to be 0.01 y of 0, but we know the generic or the general structure of that. That's a to the capital N y of 0. And now it didn't matter where we started. We can now still solve for capital N. We can divide out y of 0. We're assuming we have a non-trivial problem. So y of 0 is something. And we want to know, what is capital N. Now we know that 0.01 is going to be a to the n. We need to solve for capital N. And a, we know. We were given that in this particular problem. It was 0.887. In another problem, it might be 1/2. It might be 0.7. It might be something else. Let's solve for n. Or what does n represent? That represents the number of time steps to settle to 1% of our initial value. And this is why we went to math class in high school. So we can solve this. We remember how to use logarithms, right? Logs are just exponents. So we now look at, let's say, log base 10 of 0.01, since that will be pretty easy to find. That's equal. So I'm taking the logarithm of both sides of that governing relationship. 0.01 is equal to a to the n. This is now log base 10 of a to the capital N, or that's n log of a, and that log is base 10 log. Making it easier, 0.01 is 10 to the minus 2. We're doing base 10 log, so log of 0.01 is minus 2, and that's equal to n log base 10 of a. We know a, that was given. We can solve for n. Our settling time n is now minus 2 log base 10 of a, which for this problem is 0.887, and if we compute that, we find that after 38.4 samples, we will be in our 1% tube. Therefore, the system transient will take approximately 38, but it's not going to take 38. It's going to take more than that. And what's n? Capital N. It's an integer, isn't it? So we have to wait not 38.4. We have to wait more than 38. It's going to take 39 samples before we get into that tube. That's capital N. That's our number of samples. That's our settling time. So we now can say, forget the 38.4. It has to take 39 sample periods to settle. Is that the actual length of time to settle? No, that's the number of sample periods. The actual time, we need to know what the sample period is. This is 39 of those. We have to know what the sample period was, and that was buried inside the little a. I didn't tell you what the sample period was. So if that's the case, you can't tell them what the actual is. It's just 39 samples. But if they told you, then let's just call this T sub s bar. This is now the real, or the absolute time to settle. That's now this n times t, where this n is 39. And for grins, let's just pick a t. I didn't pick a t before, but I just am doing it now. Let's say that that was 0.04. Well, that's kind of a mess to compute, but 39 is close to 40, and I can multiply 40 times 0.04. Right? So I'm going to think of this as 40 minus 1, or this is now 1.6 minus 0.04. Oh, that's not too bad. This is now 1.56 seconds. That's the settling time. If, in fact, our sampling period was 40 milliseconds, 0.04 seconds. Questions on settling time. What did it require? What was crucial for our system to have a settling time? It has to be a stable system. If your system's not stable, you can't even talk about a settling time. If your system's marginally stable, which means what? Have roots on the unit circle, then you're not going to be stable. You're not going to be talking about a settling time because you're never going to settle. Never settle. You've probably heard that before. Now when you hear never settle, you can think of poles on the unit circle. Never mind. Don't say that to President Hart, please. Yes? Yes, so now if you have an actual system, if this is a continuous time system, the A matrix, the B matrix is going to hinge on the sample period that you select. And what did we say leading into this lecture with one of our goals? What did we say the sampling period might be for a generic system? 30 times the closed loop bandwidth. So if you didn't need to speed up your system and you had a continuous time system matrix, you would look at its fastest eigenvalue and say, oh, I need to sample 30 times that. Meaning if it had an eigenvalue that was the fastest at minus 10, now you need to sample 30 times 10, or 300 radians per second. That would be your omega sub s, and you can now back that out to find what t is. But your system representation in the discrete time is going to definitely depend on that capital T. For the settling time, yes, so the question was, if we start messing with the sample period, then we should see, if we haven't done anything else to our system better still maintain the same actual settling time. But the number of samples might change. So the number of samples, depending on our settling time, it might be 80, it might be 40. But the actual settling time should be the same. The real settling time. Yes? So the question was, do you have an error in this sampling period? And I think you're saying, or asking, what if you were here and then here and you didn't hit that 1% tube right at one of the sample periods? I don't think we're going to have to worry. In a real system, it's probably not going to be that important if you're within that one sample period range. But yes, you have this You would have to actually wait until you did get into that 1% tube before you could really claim that you've settled based on that sample period. So, so if you cut the sample period in half, your number of samples would double, but your actual time would still be the same. If your boss said, "What's your settling time?" and you said 3 seconds, and they go, "Okay, well, I want you to clean or reduce the sample period," your settling time really hasn't changed unless you do something else to your system. So now, okay, so now the settling time, yes, the question was, wait a minute, that's not quite true, because now we've halved our settling time, and that's true. Now we would maybe be at 1 point, whatever it was, 55, for example, or 1.54, because now we've collapsed, or we're sampling finer our system. We're more accurate maybe in terms of the behavior or the response. But you're within a whisker, okay? We're not going to worry about it. That's cutting hairs, splitting hairs, not cutting, splitting hairs. Cutting hairs are easy. Splitting hairs are more problematic. Yes? Never mind. Let's move on. Let's move to block diagrams. We're covering some material today, and maybe not enough. I need to speed up. Let's look at a block diagram and an all-delay block diagram, or how we might build one. Suppose that somebody now gives you the following difference equation. W sub n plus 3 W sub n minus 1 plus 2 W sub n minus 2 is equal to, let's say, some reference input R of n. And all systems do not have coefficients of 1, 2, and 3. Those are easy. Okay? But you can go home and play with another napkin and have different coefficients. This is actually an unstable system, isn't it? You already know that. Has roots of -1 and -2. You can go home and have a stable system. I'm just doing this so that we can see where these coefficients appear in our block diagram. To build a block diagram, what we do is we solve for the highest index of n in our dependent variable, W of n. In this case, we have W sub n is R of n minus 3 W of n minus 1 minus 2 W of n minus 2. If I'm building a block diagram, an all-delay block diagram, how many delay blocks would you anticipate I need in this all-delay block diagram? You look at the highest index, n, and then you look at the smallest index, and what separates those? 2. So you need 2 delay blocks. You need to delay twice in order to get from W sub n to W sub n minus 2. You need a W sub n minus 1, you need a W sub n minus 2, and you need an R of n to build or to create W of n in this block diagram. We need 2 delay blocks or 2 delay elements. And really what we're trying to do is we're trying to create W sub n out of the right-hand side. So this W sub n is actually going to be the output of some SOME, summing, SUMMING, junction. Too many sums, right? But what happens if we pass W of n through a unit delay? What comes out the other side? W where? one time step before, which is n minus 1. So this is w of n minus 1. What happens if you delay that with a unit delay? What comes out of the output of that unit delay block? And we're assuming we have access to R of n. If we now have R of n, we want the inputs to that summing junction to create W sub n, and we now have access to W of n minus 1 and W of n minus 2. It's not very hard, is it, to build an all delay block diagram? This is easy. Yes? Yes, so this would just be, the question was, would this be like a register or something that holds a value for one sample period? Yes. It's just sitting there holding a value, and then it will spit out the value. Yes, it needs to be available one cycle later. So the clock is ticking. And when it ticks, you're assuming that you have W of n minus 1, W of n minus 2. So all of these are stored in some register. Meaning, we now want to create W sub n. We need to take W sub n minus 1 and scale it with minus 3. We already have R of n, and we need to take minus 2 and use that to scale W of n minus 2. And we're basically finished with our block diagram. Somebody hands us a linear difference equation, you can now create an all delay block diagram. Not very difficult, was it? Let's now create a state space representation in discrete time. And the only thing that you need to do now is label the outputs of the delay blocks as state variables. How many state variables do you have for this system? How big is your state vector? Your state vector is so many rows tall, and it's just one column wide. How many state variables do you have? How many delay block outputs do you have? How many delay blocks do you have? That's how many delay block outputs you have. You have 2 delay blocks. You should have 2 state variables. So we have a state 1, x sub 1, and a second state, x sub 2, and it's somewhat arbitrary how we pick those. Let's just call this x sub 1 of n. That's the output of one of our unit delay blocks. And let's call the other one x sub 2 of n. That's the other output of our delay block. Meaning, to find a state space representation, we simply define outputs of delay blocks as state variable components. Where we have component 1, we're calling x sub 1, and component 2 is x sub 2. Now we're doing difference equations, or discrete time state space. We now want x time n plus 1 equaling some matrix A, or we'll call it phi, so that we don't get confused with continuous time A matrices. We'll call it a phi. We want to go Greek, okay? Change up the alphabet a little. So we'll have phi times x at time n plus gamma times the input. Okay? Meaning, we now want to find or build an equation for x sub 1 at n plus 1. Where do we find x sub 1 at n plus 1 in this block diagram? Is it there? I see x1 and x2. No n plus 1, but what it's hiding, isn't it? but it's there in plain sight. It's hiding in plain sight. If x1 at n is a delayed version of what? X sub 1 of n plus 1. X sub 1 of n plus 1 is actually this same signal right there. Here is x sub 1 of n plus 1, and I think I heard that. It's x sub 2. Where is x sub 2 of n plus 1? It's the input of the delay block that we labeled as x sub 2 of n. So x sub 2 of n plus 1 is right there. Questions on that? Now we should be able to write x sub 1 of n plus 1 as something times x sub 1 of n plus something times x sub 2 of n plus something times, whoops, typically that will be u of n, but in this case it's r of n, our reference input. And we want to fill in these blanks. It can't be a function of some advanced or delayed version of our state variables. They have to be x1 of n, x2 of n, x3 of n, x4 of n, and r of n. Can we fill in these blanks? What is x sub 1 of n plus 1? This is so easy, it's hard. It's just x sub 2 of n, right? It's the same signal. What's x sub 2 of n here on the right-hand side? Well, we need none of that. We need one of those, and we need no r's. Those are our blanks filled in. We needed x sub 1 of n plus 1 to equal x sub 2 of n. The other state variable equation or component, x sub 1 of n plus 1, maybe is a little bit more interesting. By that I mean maybe it's has more content. What is x sub 2 of n plus 1? We want to write that in terms of x1 of n, x2 of n, and r of n. No n plus 1s allowed. What's x sub 2 of n plus 1? Do you want me to do the easy part? I see an r, right? We just look at all the signals coming in to that summing junction. The output of that summing junction is x sub 2 of n plus 1. That equals the three signals coming in. One of those signals is r with a scaling of 1. Another one is minus 3 times what? Was that scaling x sub 2? And we had a minus 2 scaling x sub 1. Wow. Now we have a state space representation, a discrete time state space representation. We can now write this in vector and matrices form, meaning we can now have x1 of n plus 1 stacked on top of x sub 2 of n plus 1. And that's going to equal some system matrix phi, which is going to be square because it's going to multiply x1 of n, x sub 2 of n, and its result is going to produce 2 rows. So it's 2 by 2 plus an input matrix times r of n. And we'll call this input matrix. Here is our system matrix. Here's our input matrix. That's going to be gamma. We'll say that's our input matrix. Do you see how to fill in the blanks of phi and gamma based on these two coupled difference equations? We just have to make sure that our matrix multiplication is accurate. In the first row of the A matrix, what do I see? We need to just pull off x sub 2, and we do not want any input. So the B matrix, the input matrix, which is gamma, is 0. What about the second row of the phi matrix, the system matrix? -2 and -3, and the bottom row of the input matrix gamma is 1. That's how it's populated. You now have the system matrix and the gamma matrix. What's the output matrix for this block diagram? I don't know, you didn't define it. We didn't, did we? We didn't define an output. Let's just pick one. Let's just say it's this. Let's say that's y. If that's now our output, let's build up the output equation. Y of n is now some linear combination of our state vectors at the current time n plus, in general, some direct feed-through of the input r. This we will call, just to mix it up a little, this is our output matrix. Let's call that H. And let's call this J. This is our direct feed-through matrix. What do we want H and J to equal if our output Y of n is equal to X sub 1 of n? Is R in there? No. So it's 0. A lot of times your direct feed-through matrix will be 0. What's the output matrix H structurally, or what are its elements? It's a 1 by 2 row vector. It's 1 row tall, 2 columns wide. It just needs to pick off x1 from the state vector, x1 and x2. It's now going to be 1, 0. Now, if you're playing along, you've probably already figured out what the eigenvalues of phi are. Yes? No? If not, we can find them. What they will be, those will be the natural modes of our system. And we've already found those before because I stuck with the difference equation, W of n plus 3 W of n minus 1 plus 2 W of n minus 2. Or notice that eigenvalues of our system matrix phi equal -1 and -2, which were the roots of the characteristic equation. If you've forgotten, the eigenvalues are simply what? The values of lambda that satisfy the determinant of lambda I minus phi equaling 0. Or what is that? We now have lambda I. We know what phi is. We now take lambda times I. I is the identity matrix, and it has to be the same size as phi. Phi was 2 by 2. And we need to find the determinant of that expression in terms of this variable lambda. Or this is now lambda in the 1, 1 entry minus 1 in the 1, 2 entry, 2 in the 2, 1 entry, and lambda plus 3 in the 2, 2 entry. You need to be able to find a 2 by 2 matrix's eigenvalues. On an exam, maybe a 10 by, no, not a 10 by 10, but you better be able to do a 2 by 2. This is now the product of the diagonals minus the product of the off diagonals. We have lambda times lambda plus 3 minus 1 times 2, or this is now lambda squared plus 3 lambda plus 2. That's our characteristic polynomial. The characteristic equation is when we set that equal to 0. Whoops. And that factored form hasn't changed since Wednesday. This is now lambda plus 2, lambda plus 1 equaling 0. Or one of the lambdas is minus 1, the other lambda is minus 2. And those are the natural behavior. If we came and set some initial conditions on our system, it would naturally want to shake at minus 1 and minus 2 as its modes. Or it's going to go unbounded because of that mode of minus 2 outside the unit circle. Now, I said we don't just play in the time domain, do we? We're electrical engineers. We need to be able to play not only in the time domain, but also the frequency domain. Well, now how do we do that? Well, it's pretty easy in block diagram terms. In block diagram terms, we simply replace those unit delays with 1 over z, or z to the minus 1. And that now introduces this frequency variable, which we will learn more about. But let's just draw the block diagram, or remind ourselves that we want, yes, we also want to analyze discrete time systems in the frequency domain. Where now our block diagram is created by simply replacing the delays, which are in the time domain, with this frequency domain operator, z to the minus 1. This is our time domain, and this z is our complex frequency variable. The other thing that we do is we no longer have the ends in our arguments. Now we replace those with a square bracket, and we have arguments of z, the complex. Now we're in the frequency domain, meaning we now have 2 blocks that contain z to the minus 1s, delays, in the frequency domain. We could say here is our air signal in the frequency domain. Here is our reference, r of z, but now all of the other pieces are the same. We have a minus 3, and we have a minus 2. And this is now, let's say, our output in the frequency domain, y of z. What we want to be able to do is find the transfer function. Now that we're in the frequency domain, we're over here. We're no longer dealing with difference equations. Now we want transfer functions. We want ratios of y of z over r of z, and we can find that for the 441, 541 students using Mason's gain. For For everyone else, for anyone else, you can do block diagram algebra. It doesn't matter. Let's do some block diagram algebra. We have plenty of time. Somebody said we'll start early and stay late. We're doing that. Everybody has caffeine. I saw that before class, right? 2 liters of it. So you're good to go, other than maybe if you need to go to the restroom, that's okay too. But let's do just some block diagram algebra. If you're patient. I think we have this room reserved all night. Block diagram algebra. We can solve for E, which is the output of this summing junction. E of Z is now R of Z minus, do you see it's minus 3 Z to the minus 1 E of Z? And it's also minus 2 Y of Z, but Y of Z is Z to the minus 1, Z to the minus 1 E of Z. I'll finish this up after class. I'll let you go. I know you have places to be, people to see, so I'll release you, but I will show you hopefully after class in the notes how to find the transfer function between the input R of Z and the output Y of Z, simply doing algebra with the block diagram. It's not that hard. So that will be in the notes, and I will see you in 2 days this time on Wednesday. Have a good rest of the evening. Passport is due, and homework is due in a week.